Okay, so picture this. You pull into a grocery store parking lot, and it is absolutely jam-packed. Cars everywhere, right? But how do we actually know when a parking lot is full? Like, what even is full?
Hmm.
It seems like kind of a simple question, but I think it reveals something pretty deep about how we understand the world.
Yeah, and it's interesting because we often aim for these, absolute values in measurement, but we're almost always actually dealing with approximations.
Right.
It's kind of like we're using prototypes, these like
Yeah.
representations of the ideal.
Prototypes. Can you give me an example of that?
Oh, absolutely, yeah.
Yeah.
So think about absolute zero, right? The lowest possible temperature. It exists, like in theory, but actually reaching it like physically is really difficult.
Mm-hmm.
It's this ideal we're striving for, but we can't ever quite get there.
Mm.
Or, another one is irrational numbers, right? Like pi.
Right.
We use approximations of it every day, but that infinite string of digits is ultimately unattainable. Like we can't write out the entirety of pi.
So we create these like prototypes to have as like a stand-in for this absolute.
Precisely.
Yeah.
And the interesting thing is that even our prototypes, like they evolve over time. A great example of this is like the very definition of a meter.
Wait, so you're telling me like a meter isn't always a meter?
Well, yeah, it might sound strange, but the way we actually define a meter, it's changed as our tools and our understanding of the universe like gets more and more sophisticated.
Okay.
So originally a meter was defined as 1/10 millionth of the distance from the North Pole to the equator.
Oh, wow.
Yeah.
That sounds tough to measure.
Not exactly something easy to measure, right?
Yeah.
Now, we define a meter by how far light travels in a vacuum in a teeny tiny fraction of a second.
Wow.
So this new method is incredibly precise, but it's still relative to something else,
Yeah.
right? The speed of light, which of course we've agreed on as a constant.
So even our most fundamental units of measurement, they're based on these like agreed upon standards, these prototypes. That's kind of wild.
Yeah, it is. And it actually gets even more interesting. So for the longest time, the kilogram was actually defined by a physical object.
Really?
Yeah.
What do you mean?
It was a cylinder of platinum iridium alloy, and it was kept under lock and key.
Hold on. So a physical object, like this is the kilogram.
Exactly. And this like really highlights how important these reference points are. I mean, they ensure that we have consistency in our measurements even as like our understanding of the universe changes.
So how does all this like connect back to our parking lot problem?
Well, it means that even something as like seemingly simple as like figuring out if a parking lot is full, it's actually rooted in this whole complex system of measurements.
Mm.
And each of those measurements is relative to some kind of agreed upon standard.
Okay.
And we often just don't even realize it. Like
Yeah.
all of that thought and all of that like precision that goes into the measurements that we just like encounter every single day.
It's like we're peeling back these layers of like reality, and then we find this whole hidden world of prototypes and calibration and
That's a great way to put it. We're kind of uncovering the framework that lets us make sense of the world around us. We can compare things, we can quantify things in a way that's consistent and meaningful. And a big part of that is understanding that measuring something is never absolute. It's always relative to something else.
right.
And this whole idea of relativity is really key to interpreting all of the data that we encounter in our lives.
So you've talked about how measurement is more complex than it seems, but how do we make sure that those measurements are accurate, when we're actually like taking them?
Right, right. Yeah. And it brings us to this really important idea of calibration. It's basically the practice of comparing a measurement instrument against a known standard, something that we already know is accurate.
Okay, so it's like a way of double checking that our tools are giving us the right readings.
Exactly. Think about a bathroom scale, right? Like the one you probably have at home.
Okay.
When you step on it, you're not actually directly measuring your weight, like in some kind of absolute sense.
Yeah.
What you're really doing is comparing your weight to a reference point. And that reference point has been calibrated using weights that can be traced all the way back to that super carefully protected kilogram prototype we were talking about.
Right, right. It always comes back to the prototypes. But how does that work with something more complex than a scale? Like, what about an instrument that measures voltage instead of weight?
Well, the principle is actually pretty similar. Let's take a differential amplifier as an example. It's this device that's used a lot in electronic measurement systems. And it basically acts like a scale, but for voltage instead of weight.
Okay, I'm intrigued. Differential amplifier sounds kind of intimidating, though. I'm not going to lie.
Yeah, no, I get it. It sounds complicated, but it's not too bad once you break it down. Basically, a differential amplifier compares two input voltages. One of those voltages is the unknown voltage, the one we're trying to measure, and the other is a known reference voltage, something that we already know the value of.
So it's like comparing an unknown weight to those calibrated weights on our scale.
Exactly. And then the amplifier tells us the difference between those two voltages. If there's no difference, then we know that our unknown voltage is equal to our reference voltage.
That makes sense. But how do we go from comparing voltages to getting an actual number, like a digital readout, especially in a world where everything seems to be digital these days?
Yeah, that's a great question. And that's where analog to digital converters come in, or ADCs for short.
Mm.
These things are pretty cool. They take that continuous electrical signal, which represents our measurement, and they convert it into a digital signal, a bunch of ones and zeros that computers can understand and display.
Okay, so the differential amplifier is like our electronic scale, and the ADC gives us a digital readout of the measurement. But where does physical calibration fit into all of this high-tech stuff? Like, do we still need it even with all of these fancy electronics?
That's an excellent question.
Yeah.
And the answer is yes, we absolutely still need it. Even with these really advanced electronic systems, we still have to make sure that they're measuring what we think they're measuring and that they're doing it accurately. That's where those physical standards come in, those calibrated weights we were talking about earlier.
Really? So even when we're making these really sophisticated electronic measurements, we still rely on those carefully calibrated physical weights.
Absolutely. Those weights, which are traceable back to that international prototype
Yeah.
kilogram, they're used to make sure that the entire measurement system is accurate, from that initial voltage comparison all the way to the final digital readout that we see. It's a really good example of how the physical world and the digital world are completely intertwined when it comes to measurement.
Wow. It's just amazing to think that like all of our measurements, even the really high-tech ones, all come back to these like physical objects, these standards.
Yeah, it really drives home how important this whole calibration thing is.
Yeah.
We've got to make sure that our measurements are accurate and reliable, especially now, when it seems like everything is digital.
So it's not even just about the instruments themselves, right? It's like this whole system, this whole chain of calibration that makes sure the measurement actually means something. But like, how much does this actually affect us in our everyday lives? I mean, I get it for like, scientists in a lab with their scales and stuff, but what about the rest of us?
Oh,
Yeah.
no. I mean, this stuff is everywhere. We just don't always think about it. Like, take medical devices, for example.
Right.
What if you had a blood pressure monitor that wasn't calibrated correctly?
Hmm.
Or like a glucose meter?
Yeah,
That could be really dangerous, right?
that's true. Yeah.
Or even something as simple as the scales they use at the grocery store to weigh your produce,
Okay.
even if it's off by a little bit. Those tiny errors, they add up over time.
Yeah, that's a good point. It seems like really understanding calibration, like how important it is, and how it makes sure measurements are accurate. It's got to be even more important now than it used to be, right? I mean, think about how much data is out there these days. And speaking of data, I was thinking about our author, William Weaver. He really seems to get this connection between science and technology and data.
He really does.
Like his background is super interesting.
Yeah, and it really gives him a unique perspective. I mean, he's an associate professor in integrated science, business, and technology, right?
Right.
And on top of that, he specializes in ultra-fast laser spectroscopy.
Wow.
So, yeah, he understands how complex scientific measurement can be, but he also gets how important those measurements are in all sorts of different fields.
Yeah, it's like he's bridging the gap or something. Like between that world of prototypes that we were talking about, those like ideal measurements, and then how those measurements actually play out in the real world, with real data.
Absolutely. And something that's really important to him is making sure people think critically about data. Like, we're just bombarded with numbers and figures all the time now.
Right.
But we can't just accept them, just take them at face value. We got to understand, like, what's the context here? How was all this data collected? How was it analyzed? Were there any biases, like in the way it was presented?
So it's like we need to calibrate our own internal BS detectors or something whenever we see some new data.
Uh-huh. I like that. Yeah. It's all about asking the right questions. Like, where did this data even come from? What methods did they use to collect it and analyze it? And like you were saying, what are the assumptions that might be hidden in the way that it's presented to us?
Right, exactly. It's like that saying, what is it? Torture the data long enough and it'll confess to anything.
Uh-huh. Right.
Like, we can't just jump to conclusions. We got to understand the bigger picture.
Exactly. And as we rely on data more and more, which is definitely the direction things are going, it's going to be more and more important to think critically about it. We've got to be savvy about the information that's coming at us.
Yeah.
Whether it's a big scientific study or an article
Yeah.
we read online, or even just like a social media post.
So as we wrap up this deep dive, what's the one thing you hope our listeners take away from all of this?
I think the biggest thing is just to remember that even something as seemingly basic as a measurement, there's often a really fascinating story behind it. Like a lot more going on than you might think. Don't be afraid to be curious. Question those numbers you see. Dig a little deeper. You might be surprised by what you find.
I love that. This has been a fascinating look at the world of measurement and calibration. We learned that even the simplest things in our lives rely on this, like hidden web of precision and agreement and this constant drive to be accurate. And as we keep learning more and more about the universe, you know who knows what we'll discover next. So keep those BS detectors calibrated, everybody. Stay curious, and we'll catch you on the next deep dive.